Hi everyone. In the last video we have discussed different representation of the complex number like algebraic representation of the complex number, geometrical representation, trigonometrical representation. So similarly we will see this exponential representation of the complex number. So if we recall all these representation, so when we write z is equal to x plus iy, so we say this is the algebraic representation of the complex number. Similarly, if you plot it on the x and y axis, suppose this is your x axis and this is y axis. So along x axis, as we have already discussed, we plot the real number, and along y axis we plot the imaginary part or the imaginary number. So here x will be plotted along this, y will be plotted along this. So if this is your z, then we will have this coordinate of this z as x, y. So this part it represents x and this part it will represent y. So this we say it is the geometrical representation of the complex number. And similarly, if you consider this distance as r, so this is O and this angle as theta, and this theta is your argument or the amplitude. So, and this distance is r, which is termed as the magnitude or modulus of the complex number. Then this part it becomes r cos theta and this part it becomes r sin theta. It means x is r cos theta and y is r sin theta. So if we plot it here, so z is equal to, that becomes r cos theta plus this I sin theta. So r is the magnitude of this z, theta is the amplitude or argument of this complex number. So this is the trigonometrical representation. Now we will see this exponential representation. This exponential representation is also termed as Euler's theorem. So here this cos theta plus I sin theta, it is assigned an exponential value, and that is e to the power I theta. So here you can write e to the power I theta, it is equal to cos theta plus this I sin theta. It means this trigonometrical form, it is just replaced in the exponential form and it becomes e to the power I theta. So here if amplitude or argument, if it is theta, then that is in the power of this exponential function, that is e. So here we have e to the power I theta. Now if you multiply by the magnitude, so this exponential part it will also get multiplied by this r. So r e to the power I theta, and that becomes your r cos theta plus I sin theta. Now, so this is just the representation. If you increase or decrease the value of this theta, or in general if we change the value of theta, corresponding to that here also the theta will change. If you make it as suppose r cos n theta plus this sin n theta, then this can be represented as r e to the power I n theta. So whatever is the term here, it will appear here. So that way we can have the exponential representation. It is also termed as the Euler's formula, or it is termed as Euler's theorem. Now from this Euler's theorem or this exponential relation or exponential representation, we get another concept which is called de Moivre's theorem. Just from this only we get this de Moivre's theorem. Now when we consider this de Moivre's theorem, so it is nothing but cos theta plus I sin theta. That is represented as what? E to the power I theta. So cos theta plus I sin theta to the power n, it will be represented as what? E to the power I n theta. Cos theta plus I sin theta, that becomes what? E to the power I theta. Now if it is raised to power n, so this will also be raised to power this n. So that here you will get e to the power I n theta. This is clear. Now there is the relation given by again this de Moivre's, and just because of that it is termed as de Moivre's theorem, that cos theta plus I sin theta to the power n. That means cos theta plus I sin theta, it is multiplied how many times? N times. Cos theta plus I, because it is raised to power n, so cos theta plus I sin theta into cos theta plus I sin theta into cos theta plus I sin theta, how many times? N times. So it means here, if you remember the product of the complex number z1 into z2, so if z1 is suppose r cos theta 1 plus sin theta I sin theta 1, if suppose z1 is, let us say z1 is equal to r1 cos theta 1 plus I sin theta 1, and z2 is r2 cos theta 2 plus this I sin theta 2. Now if we multiply this z1 and z2, so we get z1 z2, that is r1 r2 into this. Now if you recall, so cos theta 1 plus I sin theta 1 into cos theta 2 plus I sin theta 2, when we multiply, we got that the magnitudes are multiplied. When the two complex numbers are multiplied, the magnitude of the complex numbers get multiplied, but the amplitude or argument that gets added. So here if you consider this z1 z2, so that will become r1 r2, and here it will become cos theta 1 plus theta 2 plus I sin theta 1 plus theta 2. So it is multiplied, the magnitude it is multiplied, but the amplitude or the argument it gets added. So cos theta 1 plus theta 2 plus I sin theta 1 plus theta 2. So that way we represent as far as the product of the two complex numbers are concerned. Here we will use the same logic. Here it is multiplied how many times? N times. Cos theta plus I sin theta to the power n. It means this argument theta, it will be added. So theta plus theta how many times? N theta, and that becomes n theta. So cos n theta plus I sin n theta. So cos theta plus I sin theta to the power n, simply multiply the amplitude or argument by this power n, and we get new complex number which is equal to cos n theta plus I sin n theta. Now we have some particular case of this. If n is a positive integer, then cos theta plus I sin theta to the power 1 upon n, that becomes your, this is the general solution. Cos 2k pi plus theta upon n plus I sin 2k pi plus theta upon n. Here it is 1 by n, so obviously here it is n, so it is multiplied by n. Here it is 1 upon n, so it will be 1 upon n. Now 2k pi, it is just a general representation as far as the argument or amplitude is concerned. Now obviously k is equal to your 0 to this n minus 1, all these are integers. Now the value corresponding to k is equal to 0 is called the principal value. Obviously when we remove this, so this theta become k is equal to 0, so this part will no more exist. So this becomes simply this theta, and that theta is nothing but the principal value. That's why we say 2k pi plus theta, that becomes your general solution or the general value. So now here again, this is another property, that this theorem is valid even if n is any rational number. N is any, not only integer, if n is any rational number, then this theorem works. So okay, now so it means from this, as far as this concept and this concept is concerned, from this you can conclude de Moivre's theorem, it is nothing but when we multiply two complex number like z1 and z2, so we got amplitude or argument added, theta 1 plus theta 2. Similarly, if you multiply three complex number, it will be theta 1 plus theta 2 plus theta 3. If we multiply n complex number, it will be theta 1 plus theta 2 plus theta 3, theta 4, and so on. Here theta for each complex number it is same, so theta plus theta n times, so that becomes your n theta. So if you have z is equal to cos theta plus I sin theta to the power n, directly we can write z is equal to cos n theta plus I sin n theta. If r is the magnitude, then here also it will be multiplied by r. Otherwise, if it is not there, it means the coefficient here it is 1, here also it will remain same as 1. Now let us see some illustrations based on this. So if we come back to this Euler's theorem, now if we come back to this representation as far as the exponential representation is concerned, now suppose we have cos theta plus I sin theta as e to the power I theta. Now this relation is used to solve some of the complicated geometrical problems. Like suppose you have circle. Okay, here this is the center of the circle and R is the radius. So obviously R is same for each and every point. If you consider this distance from the circumference, any point. So this is R, this is R, this is R, and so on. Now suppose you have this complex number Z here. This is your O, and let us say this point is P. OP, it is your complex number Z. Now if you rotate this complex number OP through some angle, suppose alpha. Okay, and here this Z is, let us say Z is equal to cos theta plus I sin theta, which is equal to your e to the power I theta. Okay. Now if we rotate this complex number, suppose this OZ, and we get this this OP, and we get another complex number, let us say OQ. It means obviously this argument or the amplitude of this complex number, it is different from this. So we will get a new complex number, and that is OQ, and suppose it is Z dash. Okay. So how to calculate this Z? So if you consider the geometrical method, the situation becomes complicated, the solution becomes very complicated. So here, instead of going into the geometrical solution, we will try to use this Euler's formula. So now this is rotated through this angle alpha. So if it is rotated through angle alpha, we get the new complex number OQ, that is Z dash. So can you say this Z dash, it is equal to cos theta plus alpha plus I sin theta plus alpha. Because here argument or amplitude, it was theta, so we had cos theta plus I sin theta. Here argument for this, it is already theta. Let us say you have this axis, x-axis. Okay, let us say this angle is already theta, and that's why we have cos theta plus I sin theta. Now from here, it has been rotated through this angle alpha. So with respect to x-axis, this total angle becomes how much? Theta plus alpha. It means the amplitude or argument of this complex number Z dash, it becomes your theta plus alpha. So we get Z dash equal to cos theta plus alpha plus I sin theta plus alpha. Now here you can see one thing remains common as far as this Z or Z dash is concerned. Magnitude of this Z or magnitude of Z dash, that remains same, because this is the magnitude of Z which is equal to radius of the circle. This is the magnitude of Z dash, which is equal to the magnitude of this Z dash or the radius of this circle. That radius, or in general the magnitude of these complex number, has to be same. Then directly we can use this relation, or we can take help of this Euler's relation, that cos theta plus I sin theta and Z dash equal to cos theta plus I sin theta plus alpha. So here can we write this is equal to e to the power I theta plus alpha. Z dash is equal to e to the power, because here amplitude or argument is theta plus alpha. So Z dash is e to the power I theta plus alpha. Here it was theta, so it is e to the power I theta. Here it is theta plus alpha, so it is e to the power I theta plus this alpha. So that way we can calculate, or we can change from the trigonometrical to the Euler's relation. Is clear? Now if we consider the magnitude, then Z, we can consider this as R. So here also you can put this R. Here this magnitude, that remains same for Z dash also. It is R cos theta plus alpha plus I sin theta plus alpha. So Z dash, it will be equal to R e to the power I theta plus alpha. So that way we can consider. So now, so one complex number, the coordinate of one complex number or the argument of one complex number is known. rotating that, the condition is what? Keeping the magnitude constant, because we have kept the magnitude of this constant. So keeping the magnitude constant, we are rotating through some angle alpha so that we get a new complex number z dash. From that we got z dash equal to r e to the power I theta plus alpha. Now can you write this as r e to the power I theta into e to the power I alpha? Because e to the power I theta plus alpha, so that becomes your r e to the power I theta into e to the power I alpha. Now r e to the power I theta, this is equal to what? This is equal to this z. So from there can we conclude this z dash is equal to z into e to the power I alpha. Z dash equal to z e to the power I alpha, because this is same as this z. Now we got a new complex number z dash after rotating z through this angle alpha. In which direction? In the anti-clockwise direction. So we got z dash equal to z e to the power I alpha. This e to the power I alpha, it is termed as operator. Okay, z dash equal to z e to the power I alpha, it is termed as the operator. It means instead of alpha, if you rotate it through beta, suppose you have rotated through this beta, this angle is beta, we will get z double dash, and that will be equal to how much? E to the power I alpha plus this beta, r e to the power I alpha plus. Okay, so we have z double dash, it is r e to the power I theta plus this beta. So from here z dash z e to the power I alpha, from this you will get z double dash is equal to z e to the power I beta, because this complex number we got after rotating this z through how much? Through this angle, this beta. So here we keep on changing the value of this alpha, beta, gamma, delta and so on, and we keep on getting the new complex number. So instead of getting into the geometrical form of this, we can use this Euler's relation to get the coordinate or the value of the new complex number, which is achieved by rotating some complex number either through some angle alpha or beta or gamma or so on. So just to summarize this, here we can say you have this circle, we have this z, we have another z dash, we have another, suppose z double dash, this angle is theta, this angle is your alpha, this angle is suppose beta, this total angle is beta, this one is beta. Okay, so z double dash we got after rotating z through this beta, z dash we got after rotating z through alpha. So from this you can say, and this angle, initial angle is what? Theta. So z dash, it is equal to z e to the power I alpha. Z double dash we get z e to the power I beta and so on. Okay. So here this is the operator, here this is the operator, you keep on changing this value and you will get the new complex number. Here we have rotated in the anti-clockwise direction, that's why we are getting this plus alpha plus beta. If you rotate it in clockwise direction, let us say it is z triple dash, okay, and this angle after rotating this z, this one through angle this how much? This angle, we have rotated this through suppose this gamma. So this angle will be equal to how much? This was theta, this entire it is this gamma. So this part it will be equal to how much? Gamma minus this theta. If this is completely, if it is suppose gamma, then this part it will be equal to your gamma minus this theta. It means now when we rotate it in the clockwise direction, we get that with the minus sign, because the entire angle get decreased. Here angle, when we rotate this side, angles are increasing theta plus alpha, theta plus beta, and so on. Here it becomes theta minus gamma. So in that case, you will get this z triple dash is equal to z e to the power minus of I gamma. So when we rotate it in the anti-clockwise direction, there you will get alpha beta with the positive sign. If you rotate it in the clockwise direction, you will get this gamma with the minus sign. So that is the only significant, and there is nothing to remember in this, because anti-clockwise rotation, obviously the angles will keep on increasing, so there will be positivity. Clockwise rotation, the angles will be decreasing, so there will be negative sign. So that way we can analyze all this. Now it is not only that, because there is only one condition, that the magnitude of the complex number remains same. Suppose length of this, if it is constant, I can rotate it and I can keep on getting the new complex number. Is this clear? That is the only condition required, and this gives a very simple solution as far as comparison with the geometrical method or geometrical solution is concerned. If now here we are using this, or we have used this in circle. Similarly, you can use this in case of isosceles triangle, because here also these two sides are same. So wherever there are same length of the sides, there we can always use this Euler's relation. So here two sides are same, so if it is rotated, we will get this one. Similarly, if it is a case of suppose equilateral triangle, length of all the sides are same, so rotating this we can get this, rotating this we can get this, because the length only or the distance that has to be same. That is the only condition. Otherwise, whatever angle you rotate, whether in the clockwise or anti-clockwise direction, we will keep on getting the new complex number. Simply use this operator and you will get the value of that. Okay. Similarly, we have isosceles, equilateral. Similarly, you can say regular hexagon, or in general regular polygon. Here also the length of the sides it remains same. So in this case also we can use. So wherever you find the length it is same or the distance it is same, try to use this method. If it is applicable, use it. If it is not applicable, then only go for the geometrical method, because that is always the calculation part in that method is always complicated as far as this relation is concerned. I hope it is clear. So from next video or next lecture, we will start discussing problems based on the complex number. Thank you.